term in the rocket engine. The exhaust velocity of a rocket engine is quoted and calculated unit of meters per second. In rocket engineering, the exhaust velocity is almost universally quoted in terms of the specific impulse. The apparent unit of specific impulse are seconds, and the equation relating specific impulse to exhaust velocity is Be equal to g into ISP. G is the acceleration of gravity in metric units. G is close to 10 meter per second. So it is sufficient when faced with the velocity quoted as specific impulse to multiply by 10 to express in terms of meter per second. There are three reasons for this usage. The first is historical, and as astronomers know, it is difficult to change the historical usage. The second reason is that the apparent units of specific impulse being seconds, it takes the same value in the metric and imperial system. The actual exhaust velocity emerges in the same units in which the acceleration of gravity is quoted. Remembering that until recently NASA has used imperial units, this is a useful convention. There is also a possible physical argument as follows. Impulse is the term used to describe the effect of a force applied for a very short time to an object, as in, for example, the contact between a bat and a ball. The product F dt is equal to the momentum given to the object. The specific impulse is defined as the impulse given to the rocket by unit weight of the propellant. The specific impulse is defined as the impulse given to the rocket by unit weight of the propellant, where m is the convention in the mass flow rate. Real units of specific impulse are Newton seconds per Newton or kilogram meter. The specific impulse can be most usefully considered as a measure of the fuel efficiency of the rocket, that is, the momentum imparted to the rocket per kilogram of propellant expelled. If the exhaust velocity is high, then the propellant efficient is high, which is clear from the equation for thrust. Specific impulse is proportional to exhaust velocity and is direct measure of the propellant efficiency. It is convenient to express some of the other formula in terms of specific impulse, remembering that GISP is equal to the effective exhaust velocity VE. It would perhaps be an advantage if the confusion of units could be removed from the business of rocket engineering, and with the universal adoption of SI is achieved. A similar calculation for the Viking 4B high altitude motor, which has the same throat area but a much larger exit area, yields a value of 1.86 for the vacuum thrust coefficient. For the lowest atmospheric pressure, the expansion ratio of 30.8 shows that the thrust coefficient is not quite optimum for vacuum. The exhaust is still under expanded, and the value of the thrust coefficient corresponds to a position to the left of the appropriate peak. This is deliberate and is the result of a compromise. To make the expansion perfect would entail a much longer nozzle and a consequent increase in weight. The adverse effect of the mass ratio of the rocket would eliminate the advantage gained in thrust. These simple calculations show how the performance of the nozzles can be estimated and compared with the intended use. The characteristic velocity is the same for both rocket engines. This is advantageous since this parameter is independent for the shape of the nozzle and depends only on the conditions in the combustion chamber. These are almost the same in both cases. The effective exhaust velocity of the engine is the product of the thrust coefficient and the characteristics velocity. This will be the longer nozzle in increasing the exhaust velocity.